Hi, everyone. Thank you for joining today's session. My name is Eduardo. A couple things about myself. I'm a mechanical engineer. I have a bachelor's received from UC Irvine. I've been with Saratech for 3 years now, and I'm proficient in NX, Creo, and SolidWorks. So I had the privilege of diving into different CAD systems. And I also have experience in aircraft and spacecraft structures. Okay, so today's agenda, quick rundown here. I'm going to go through the introduction of what this presentation entails. So the title is Calculating Bay Volumes for Pressure Ventilation. I'll provide a scenario or a problem to solve during this session. I'll walk through the NX demo, show you the clicks and how to navigate it if you want to follow along on your end. And lastly, I'll recap and point out some key takeaways from the demonstration. Okay, and before I begin, I just want to mention that today is the 117th anniversary of the first flight. So in December 17, 1903, the Wright brothers made their first controlled and sustained flights. So I thought this was a nice fitting just reminder here based on what we're going to show. Okay, so the purpose of this presentation is to provide the audience here a tool to calculate volumes. And it's important specifically when you're looking at things like a turbine, a manifold, or something like a PC where you have to either vent air out or remove heat from the system. So we'll be going over different ways to do this, specifically looking at Boolean operations. There's different ways to calculate volumes in NX, but I think using Boolean operations is a great tool and makes it easier down the road. We'll also look at some analysis tools, specifically volume and area, finding the area of different cross sections. Then I'll show you the clicks in NX. Okay, so we have a scenario here where we're working with a stabilizer. So just a simple assembly of an aircraft here. And our problem is to make sure that the bays and the overall structure is properly ventilated. So there can be a lot of scenarios where there's an excess amount of pressure building up inside, either due to a lower pressure on the outside. So you want to be able to make sure that not just the entire structure is ventilated, but the bays themselves, or else they can implode into one another. So we have a venting requirement, and this is just a piece of the puzzle here. The requirement we're working on is what your vented volume is in reference to your vented area. So these are the cross-sectional areas between the bays, and it's also the holes on the outside of the structure as well. So everything gets vented outside there. So the vented volume is referring to the loft volume minus the structural volume. So the loft volume, it's given by the aero folks, and the structural volume here is whatever your components amount to. So from there, you have a vented volume. And so now you'll have to work backwards from your requirements and figure out what the cross-sectional minimums are for lightning holes and for venting holes. So your stress folks will give you your maximum, and this will play into getting your minimums. Okay, and so for this demonstration, I'll show two different parts, one assembly and one part. So the first example is going to be this aircraft stabilizer. So here we have 3 different colors, and so this is the final product of what this demo is going to look like. we want to build out different bodies so we can calculate the volumes. However, because there's substructure in those bodies, we want to account for them and get the most accurate volume output as possible. And there's another thing, you can calculate the volumes of each bay, but depending on what your assumptions are, you can kind of combine them like we're doing here. So we're assuming that these 3 bays can be treated as one, and the blue is another, and the orange is another. Okay. And now for the exhaust manifold, same thing applies, but it's a little bit different here. On the stabilizer, we're working with the IML to get our volumes. And here we're working with swept curves. So a little bit different approaches. So I want to show depending on what models you guys are working with. Okay, so let me jump now onto NX. All right, so right here we have the stabilizer, and as you can tell, let me go ahead and show those bays here. So this is what the final product is going to look like on the right-hand side there. And so I'll hide the skin here. You can see those bays. Okay. So the very first thing I'm going to do is make a mirrored assembly of the skin here. So let me go back and hide this. And so I don't have a skin on the opposite side because I want to showcase this, feature here that's not usually used. But there's a mirror assembly feature that allows you to make a copy of a part mirrored about a plane. Okay. So we'll select the component we want to mirror, and that's our 110. It'll ask us to select the plane. So I'll go ahead and click on this plane here. And since we're creating a new part, it's going to ask us to either replace the name itself or add a prefix or suffix. So I'll go ahead and add a suffix and just put -02 here. And you can specify to which location is this new file going to be saved to. Okay. Now we get this window here. And if you hover over this icon, you'll see that it's a reuse and reposition. So if I click on that and hover over these two, we have the option to have a mirror association. So I'll go ahead and click on this. And so what this would do is basically make a linked mirror body to the new part. Okay. And complete. Okay, so now we have an entirely new part on the opposite side. It's in our product structure. If we take a look at the model tree here, we see that's a linked mirror body. So if you make any changes to this side here, this right side will update. Okay, so it just makes life a little bit easier if you have a symmetrical assembly. Okay, so now that we have the our OML and IML to work with, the very first thing I want to do is within the assembly product structure, start creating our new bodies. Right. So we'll turn this guy on here so we can kind of see what colors are associated to what bays. Okay. So we'll start off with this this blue one here. So that covers the first 3 inner bays here. So I know I want to capture these 3 bays here. So I'll start with an extruded body on this surface, work my way up, and then start trimming so I get an accurate representation of the inside of that volume. So I can go and use the extrude feature, click on my surface. If nothing shows up, you'll want to change your selection filter here to entire assembly. Okay. We won't get into the specifics of the dimensions and your coordinate system placement, but just keep that in mind that when you're working with a production model, you'll want to have a purpose for all the dimensions there. So let's first create a rectangular boss. Okay. I'll change my Boolean operation to none, so that creates a body, and I want it to encapsulate those 3 bays there. Okay. So once we have that complete, let's just make this transparent to be easier to view. Okay, so now the next step here is to start creating planes along the sides here. So we have a plane which we started on the this aft spar. So we'll want to create some on these ribs here. So I'll go to my home and start creating my datum planes. And we'll use those planes again to trim. So I'm holding here and selecting this interface. Okay. Do the same thing on the top spar. Make sure I'm grabbing the right one. Okay. And this last rib here. Okay, so I have my 3 planes, so I can start using the trim body tool to cut away from this. So I'll select my target body as the extrude there, and my tool options can be either planes or faces. Just toggle through these. Okay, so we have a good outline of that volume. Now the next step here is to capture the IML. So to do that, we'll want to show the show this part here. So we'll make the skins the only thing that's shown, and I want to make a linked body or a linked sheet here, so I can use that as a trimming tool for the extruded feature. So I'll go to Assemblies, Wave Geometry Linker, click on my faces. I'll make this not associative, and I can go ahead and show all. Okay. So now I have my linked face here. And so we'll use this one more time. We'll use the trim body one more time. Click on our extruded body and our face here. Toggle through this. Okay, now we have our volume here encapsulating those 3 bays. Okay. So it looks like some of this part got cut off here. I think that was due to having the sketch too short on the upper end. Let me go back to this extrude and just bring this out. Okay, so that looks much better. All right, so the next step here is to take into account all the substructure. So to get an accurate representation of the volume, we want to subtract these all these different components here, all the ribs. So let's go ahead, make this a little bit cleaner to view. And let's start with our subtract tool. So we'll go to our home tab, down select here, and click on subtract. So the extruded body is going to be our target, and then our tools are going to be the substructure. An important thing to know when you're selecting your substructure is that you can also take into account hardware as well. So if you have fasteners, rivets, anything in here already, you can subtract those from the body and again have a more accurate representation of your volume. If it turns out red here, it means that it's outside the extruded body, so it's not going to cut it. So there's no need to grab that one. Same thing for this one. It is kind of hard to see what's behind this. So a good tool is to, you can select or left click for 3 seconds and you can see some of the options here. So this makes it easier. I have this one and I have that one. Okay. All right, let's see. There it is. Again, you select for 3 seconds, or you can right click, do select from list. And it looks like I got everything there. So I'll click OK. Now we have our volume, or an accurate representation of it. So to just view this body here, we'll go ahead and hide all and just show our subtract feature here. Right, so this is our end result. All right, so that captures those 3 bays. So let's go ahead and take a measurement and find the volume for this. So a couple ways to do it. You can go to your analysis tab, go to more and go measure body. Or if you're used to some older versions of NX, you could just go through menu, analysis, and find measure body here. Okay, we'll click on this body and you have your volume here. You can also get your area. If you have material properties assigned, you can get your mass, radius of gyration, and your weight. Okay, so we got the volume for that guy. Another useful tool when you're in the volume feature is you can also change your units. So for example, if you're working with feet or a metric system, you can go ahead and change that without changing the entire units of your part. So if you go to menu analysis and go to units custom all the way in the bottom here, and then units manager, you can select which measurements you want to change the units for. So and this works for all the different measurements here. So you have length all the way up to different stress and strains units. So we'll look at volume, and we can toggle here. And let's say we're interested in meters cubed instead of inches cubed. We can make that default unit and update it. So now next time around, when I'm taking my measure body analysis here, I'll get my results in meters cubed. So just a helpful tip there in case you're using different units. Okay. All right, so that covers the first bay. I won't go into the the repetitive action of going through the other bays here, but let me go ahead and show you what the right-hand side looks like. Okay. Let's hide this so it's easier to view, and let's hide this skin. We'll hide the length face here. And so as you can see, let's go ahead and show these. We can take the different measurements of these guys as well. And so now we have an accurate representation of our vented volumes per bay. So when you're going through this exercise, you have part of the equation now solved. You have the vented volume. Then you want to go and find your vented area. So that's all the holes here from the between different bays. So in order to find that area, we can go here, and it's easy when it's just a circle, but if you have something like an oval or something complex here, you can take the area of a curve. So if you go to, let's see, analysis, advanced mass property, area using curves, you can go ahead and say temporary boundary here and select the curve. I think it has to be in a sketch environment. Let me go ahead and do that. And just use my projection tool. There you are. Okay, so now I have my curve. And this is just so I can get a quick area result here. So I'll go back to analysis, menu, analysis, advanced mass properties, area using curves, boundary, and I can click OK, click my tolerances, and you have a couple different options here. So circle size, if it's a circle, moments of inertia, what we want here is the area. So now we have a 1.57 area for this circle here. Oh, I think that was perimeter. Go back here. Oh, yeah, that was perimeter. Okay, so area is showing up as 0. We can do that again for a different one here. Yeah. Let's see. Let's try it out with this, and then I can come back and follow up on why it's showing up as 0. It might be an issue with some units or something. Let's see if we can do this on a different circle. Okay, doesn't want to cooperate today. I'll go ahead and follow up and figure out what's going on here. Let me go ahead and do this back. So we still have some time left. Just a quick recap on the stabilizer assembly here. So again, we used some Boolean operations and some trim body features. To first start off with an extrude, we set planes as our boundary so we can trim off. We used a wavelength geometry feature for the skin on the top and bottom, so we can use those again as trimming tools. And lastly, we use the subtract tool to remove all the substructure, all the inner components there. Okay. Now, have a different model of a different approach. For example, this manifold here, you won't be able to start off with a block and then start cutting material. It's going to be difficult to do that. So to do this, my approach would be to make a copy of the body and then delete the faces using synchronous modeling, so you get the inner volume enclosed. Then from there, you can use your subtract tool and kind of work backwards. Okay. So let me pull up the model here. Great. Okay. All right. So we have our exhaust manifold here. And again, first thing I want to do is make a copy of this body. Don't want to touch any of the design. I want to be working in a different environment. That's kind of the same approach I took in the first demonstration, where I was working within the assembly model tree, not within any of the actual parts themselves. You can also have a new part and have all those bodies in there, but you don't want to be doing your analysis on your production parts here. Okay, so to make a copy of this, you want to go to your Assemblies tab. If you don't have an Assemblies tab within your modeling environment, you just go to your Application tab, click Assemblies. Okay. I'll go ahead and do wavelength. Let me backtrack there. I'll do an extracted body instead because we're within the model itself. If we're in the assembly level, we would be using the wavelength geometry feature. So let's go extract geometry. I want to extract this body here. And I want to capture the volume of these inner faces here. So I'll capture that body as well. So now we have a body sitting right on top of the other. And so I'll go ahead and hide the first one and hide the other one. And so it's just one body here. Okay, another way to check is if you highlight this, you should change your feature to solid body. You should see one selected. In this case, because there's two bodies, I'm seeing two. So that extracted body tool is taking those two into account. If you want to unite them, you can go ahead and use the unite Boolean operation. Okay, so now from here, I want to go ahead and delete the inner faces. So go ahead and click on these. All right, you might have to make multiple features. Okay, so that's one. And from there, I'll use that to delete this guy. Okay. And I can use these last four. All right, so now I have a totally enclosed body. And I can, again, turn the original one on and use that as a subtract tool. So let's first, this guy here. So let's first go ahead and subtract our target body, which is this face, and delete the tool, which is this one. Okay. And let's see. Okay, so that basically you have the inner parts of the tube there. And so we want to do the same thing now for the other body. So I'll go to my subtract tool, click on, let's see, this guy. Let's click on multiple bodies. Body to subtract. Oops. I missed a step here. Let me just backtrack. So I have, this body here that has everything enclosed, and I have the other one that has the holes in there, right? Okay. And same thing for this. I have the enclosed body, and the other one was hidden. So I think that's where the issue was. Yeah. There you go. Okay, so I can go ahead and use that as a subtract tool. I'll subtract that from the original. Now we have the inner volumes here. I'll do the same thing on this one here. I'll do subtract. It's kind of hard to grab the correct one. You can kind of see which one you're grabbing based on the circles or based on the feature name. So this one's 43, this one's 29. Okay, so I'll delete that one from this. Okay. And so now, again, I have the inner volume. I can use the same method, go through my analysis tools, go measure body, and then capture the volumes. You can have multiple selections. And again, we kind of went over, changing your units here. So if you want inches cubed, you go through your units manager and do it here. Okay, you can basically select any from there. All right, so that was the second example here. So I'll jump back to the presentation. All right, so a couple key takeaways here is we first started off with defining our IML of the volume we want to capture for that stabilizer assembly. And so that was done using a mirror assembly feature. So we created a new part using a linked mirror geometry feature. We use that part to go ahead and trim the extrusions that we created. Then from there, we use synchronous modeling on the second example, where we deleted the interfaces of our copied or our extracted body. So again, we weren't touching the production features. In some of the analysis tools here, we use the area using curves, although those they didn't work quite as well. That was one method to find the cross-sectional area. And we used the measured body tool to find the volumes.
Thanks for checking out our channel. If you like what you saw, make sure to like and subscribe down below so you don't miss out on any new videos. Follow us on LinkedIn, Facebook, and Twitter for the latest engineering news and information. And to see all of our upcoming events, please visit our website at saratech.com/events.